collaborative project funded by the Global Environment Facility and complemented by the Inter-American Development Bank and the United Nations Environment Program in 18 countries of the wider Caribbean region. The GEF Plus project offers innovative, nature-based solutions to mitigate the effects of untreated wastewater on the environment and public health. And the Central American Institute of Public Administration, ICAP, is an institution specialized in the education and training of human resources at the local, national, and regional levels. So it's a pleasure for us to be the institution in charge of facilitating this learning space. And now, our facilitator today is Eric Centeno. Eric Centeno has a PhD degree in Sanitation, Environment, and Water Resources from the Federal University of Minas Gerais in Brazil, a master's degree in Environmental Engineering from the Agro-Paris Tech University of France, and a degree in Civil Engineer from the University of Costa Rica. He has a professional experience in national and international companies related to the treatment of water for human consumption and wastewater, with projects in countries such as Costa Rica, Panama, Dominican Republic, Jamaica, and Mexico, among others. He is currently a professor and researcher at the University of Costa Rica School of Civil Engineering. His teaching and research topics are related to environmental engineering, aqueducts and sanitary sewer, wastewater treatment, anaerobic technologies, emission control, and recovery of sanitation byproducts from wastewater. So, Eric, welcome. Welcome, everyone. Thanks to be here. And now the time is yours.
Thank you very much, Luis Diego, for the introduction. I would like first to thank the organization, ICAP, and crew for the invitation. And also, I would like to thank Luis Diego and Maria Paula for their help during these sessions. As Luis Diego said, my name is Eric Centeno, and I'm going to present some of the new topics related with wastewater treatment. In this case, in this very specific case, okay, I will start sharing. Please tell me if you are seeing my PowerPoint presentation. Is it okay?
Yes, it's okay, Eric.
Okay, excellent. Thank you. Um, yeah, in this case, I'm going to present this topic called, or with the title, Biogas Production and Recovery from Wastewater Treatment. This is one of my research topics. I really think this has a huge, a great potential for the region, for our region, America, Central America, and the Caribbean, as you will see during this presentation. So we are very few in this presentation. Maybe we could just start by a little introduction from your part. That way I will be able to better direct my presentation. I don't know, maybe you can open the phone, the microphone, and introduce yourself just a minute. Tell me who you are, where you work, and what is the expectation from this module. What experience do you have with wastewater treatment, maybe? Can we start with Irving, maybe? Irving Flores?
Yes, hi. Good morning, everyone.
Hi.
I'm Irvin
Good
Flores.
morning,
I'm
Irving.
from Belize. I work as a resident consultant engineer here at Belize Water Services. So we are the national water and wastewater utility. So some of my expectations is to learn a bit more of the topic. So we are currently starting a feasibility study on biogas potential at our wastewater treatment lagoons that we have in Belize City. And so it would be very interesting to learn some of the challenges and the experiences that you have. Thank you.
Thank you very much. Thank you, Irving. Miguel Montut.
Yes, hello, good morning. Yes, I'm Miguel
Good
Montet
morning.
from St. Lucia. I work with the Water Resources Management Agency. I'm the I'm the water resources specialist at the agency, and I've been involved in initiatives regarding like projects and consultancies regarding wastewater. When I entered the agency, one of the first initiatives that I worked on was National Wastewater Policy and Strategic Plan for the island. And also I am the Jaipur focal point, and part of the country program entails an initiative to look at biogas digester system at one piggery farm in the country. So I thought that this initiative, this training session would be very timely, would sort of help to basically orient me in preparation for this project.
Thank you. Thank you very much, Miguel. Okay. Preston Prince, please.
Morning. Thank you very much.
Good morning.
My name is Preston Prince, a senior engineer at the Ministry of Housing and Water. I have a background in civil engineering and water resources management. So anything that concerns water and wastewater is always of interest to me. Currently, we are having the Coop Cross project, should be starting soon in Guyana. So it's timely to have this training at this time, of course, so we can learn more how to focus on the project that is ongoing.
Thank you, Preston. Okay, Samantha.
Yes, hello everyone. My name is
Hello.
Samantha. I work for the Ministry of Public Utilities in Trinidad and Tobago. I'm working in the Economic Research Policy and Planning Division. However, I do have some background as a research assistant in some explorative nutrient recovery technologies, working like in that field, not so much in anaerobic digestion. However, we are embarking on conceptualizing a project to hopefully recover biogas from the largest plant in Trinidad and Tobago, the Betham wastewater treatment plant. So we're trying to conceptualize, and we hope to work towards doing a feasibility study for anaerobic digestion there.
Okay. Thank you very much, Samantha. Wayne, please.
Yeah, good morning, everyone. I am Wayne Langford from Georgetown, Guyana. I attached to GWI Sanitation Department. We don't have a treatment plant at this end here as yet, but the reason for I being here is to learn what you would have been exposed to and how you deal with it. So going forward in the process, we're in the process of facilitating treatment plant construction at this end here, so we can be better able to liaise with the experts and choose the best options for our location mainly.
Okay. Thank you very much, all of you. We are going to start with the presentation. We have a really diverse group. I really like it. I think that my presentation is going to give you a more important overview of all this subject. That it's very technical, but the idea here is to give a general overview of the topic. That way you will be able to go deeper by yourself by studying. I will offer you a lot of references that you will be able to consult. Some of them I think that will be available at the ECAP website. Okay, we will see at the end of the session. And the general idea is you to learn new techniques, new methods to close loops in our systems, in our sewage treatment systems. Finally, we will keep the question at the end of the session just to go faster with the presentation. So if you have any question, please note it, and I'll try to listen to them at the end of this presentation. I think that somebody is with the microphone open. Please check if you can close the microphone. Okay, it's okay now. Perfect. So I'll start with the presentation. The content, there you have my contact. Please, if you have any question, any doubt, don't hesitate to send me an email. I try to answer to you as soon as possible. There we have the table of contents. So you can see we have a dense number of topics. Each of these topics could be covered in 2 hours. Okay, so in this case, I try to compile this material just to go to show you an overview of the topic. But I have sent a lot of bibliography and sources, additional sources, that will make you able to go deeper, okay, in each of these topics. I'll try to, I start with an introduction of this module, then we'll see the fundamentals of anaerobic digestion in the topic 2. Later, we'll see where in wastewater treatment plants we can have anaerobic digestion and which type of anaerobic reactors we can use, okay? Later, very important for our topic, we will see what are the conditions or the characteristics of the generated biogas in terms of quality and quantity, just to be clear of what we can do depending on the scale of the system. Also, we will see what are the possible routes or pathways to use and to energetically valorize this biogas, and which are the conditioning or treatment requirements for this biogas. We will see some examples of biogas use in Latin America from wastewater treatment plants, some emerging topics from the point of view of research, and an introduction just to close the topic. And remember that anaerobic digestion has a huge potential for a region to boost the sanitation, okay? As I said before, we will keep the question and comments to the end of the session. So let's start here in the introduction. My objective here is to introduce you to the topic of anaerobic digestion in wastewater treatment plants and to the different possibilities of using degenerated biogas for energetic purposes. Okay, by the end of this module, I hope you will be able to propose solutions for biogas production and use in your respective countries. Okay, in regard of the municipal wastewater or sewage, just to remember, okay, where is it produced? We have different points of production of wastewater. The most normally cited is the toilets, okay, the WC. So there we have the wastewater, the black wastewater with fecal or more fecal content, but we have other sources of wastewater. We have the showers, washing machines, and the kitchen sink. The other kind of wastewater, we usually call them gray wastewater, okay? But all of them, all gray and black wastewater needs to be treated, okay? And we have a problem linked with this wastewater, but also an opportunity. So we have problems related first with health. This is the first priority when we talk about wastewater, but also we have environmental problems, really serious in our region. Okay, maybe in some countries of Latin America, we have solved the health problem, but now we are dealing with the environmental problem of wastewater that also affect the economy. And in terms of economy, we have really important problems related with, for example, tourism. Okay, at least in my country, many beaches are polluted and many rivers are polluted with wastewater. So we have really a problem, a huge problem in our region with wastewater. However, as I expect you to learn in this presentation, wastewater can also be a resource, and we can see different opportunities to transform this problem into into benefits for our community. Okay, we will see how to do it with biogas. What is the composition of wastewater? You already know that wastewater is more than 29.9% of water and less than 0.01% of solids. But these solids is what carries a lot of problems for us in wastewater. We have among these solids chemical compounds, organic matter, pathogens also, nutrients also. We can recover nutrients, as one of our participants already knows. She is doing research, or she did research in this topic. So this is another possibility from wastewater, very interesting. We have also fats, oil, cellulose, sand that can be recovered. In our case, and the focus of our presentation is more related with the organic matter and the chemical energy of wastewater. And with this chemical energy, we can transform it in biogas, which is also chemical energy, okay? And that will be the focus of my presentation. Here we have some references. As I already said, we are going to go faster in the presentation, but you can consult this bibliography, some of them in English, other in Portuguese or Spanish. We will see that the country more advanced maybe in the world in this topic of anaerobic digestion for wastewater treatment is Brazil, okay? They have a lot of publications, they have a lot of material, really applicable material for our region, okay? No, I have also done my master degree in France, and I know that those countries have very different, a very different context. Brazil, in many things, is more similar to our countries, and they have a lot of material. For example, in anaerobic treatment of municipal wastewater, you can consult this text. Is in English, anaerobic reactors from Professor Chenicharo. We have also references specific for the anaerobic digestion of sludge, really good sources for medical and the Water Environmental Federation in English. Regarding the biogas use from wastewater treatment, we have some sources in English. This text from 2019, really good text for this topic in general. We have also some really technical guides from Pro Biogas from Brazil in Portuguese, very specific, okay, this one. And for the topic of circular economy, you can consult these texts as well, okay? Some in English, some more focused for the developed countries, okay? Other, like Chanicharo, more general for developed and in development countries as well, okay? Okay, regarding the fundamentals of anaerobic digestion, we will see that any reactor, any anaerobic reactor, it could be for municipal waste, okay, for example, fruits or agricultural waste as well. It could be for wastewater, that is our topic here. It could be also for sludge from the treatment of wastewater. We will have some steps, some stages that are common and that are the fundamentals of anaerobic digestion. Just to start with, this is a diagram that shows the fundamental differences of the anaerobic metabolism of microorganisms and the aerobic metabolism. So remember that we can have, for the wastewater treatment, aerobic reactors, and we can have also anaerobic reactors. Aerobic reactors works with oxygen. So we have a source of oxygen. It could be injection of oxygens with mechanical equipment. It could be natural aeration of the system as well, like in trickling filters. On the contrary, anaerobic reactors work without oxygen. Oxygen is very toxic for anaerobic microorganisms. So we have two general routes for the treatment of organic matter. In this case, the organic matter is measured in terms of COD, chemical oxygen demand, okay? In the case of aerobic reactors like sludge, activated sludge or trickling filters, of the 10% of the COD, the organic matter that enters in the system, a huge amount of this COD, COD is transformed in sludge between 50 to 60%. Another important percentage is transformed in CO2. Remember that in this case, we have respiration, just like we do. The microorganisms also do respirations. They transform the COD into sludge, into more biomass, and into CO2, okay? And a small fraction of the CO2 remains in the effluent, in the liquid effluent. These go to the discharge point or to reuse, if you have reuse, 5 to 10%. Very differently is the anaerobic metabolism, in this case, from the uh, a huge amount of the COD is transformed into biogas. Look, 70 to 90% is transformed into biogas. Here is where we have the energetical potential of the system. Another fraction, very small fraction, between a fifth to a fourth part of the aerobic reactor system is transformed into sludge. So only 5 to 15% is transformed into sludge. The problem of anaerobic reactors is that a larger amount or fraction of the COD entering the system remains in the effluent, 10 to 30%. So normally to meet the discharge limits in our region, you will need a post-treatment for the anaerobic reactor. Normally an anaerobic reactor as a post-treatment, but you already removed more than 70% of the COD entering the system, and you produced biogas. So see, or I just want you to perceive that from the metabolism, from the fundamental of the system, you already have two really important difference, or three really important difference. You have the production of biogas. You will have less sludge production. That is a huge part of the cost of a sewage treatment plant, the sludge treatment and disposal, and you will need a post-treatment also, okay? Regarding the stages of the anaerobic digestion, here you have a diagram of this of how it works. Look that we have many different stages. Normally, we tend to say in the academy that if you have only if you have a aerobic bacteria, an aerobic microorganism, this same microorganism will be able to degrade the organic matter, and at the end you only need one bacteria, one microorganism to have oxygen, CO2 and water. So the complete reaction is done by only one type of microorganism. This is not the case for the anaerobic reaction, for the anaerobic digestion. We will have a lot of different microorganisms. We have a very complex ecosystem in our anaerobic digestion systems. We have also a group of bacteria, fermentative bacteria, that will hydrolyze the system. So we have to break down complex organic compounds like carbohydrates, proteins, and lipids to more simple organic compounds, sugar, amino acid, fatty acids. Then we have other processes, acidogenesis, acetogenesis, where we could transform these compounds into organic acids or acetates. Okay, we have different groups of bacteria that do that. We have the formation of hydrogen here and acetates, and only in this stage we have the work of methanogenic archaea. This is a kind of microorganism also that do the methanogenesis. Just in this case, we will have the production of methane. Okay, so we have a series of stages that will be performed all of the same time in a really complex ecosystem. In the other hand, we have some competing processes. In this case, the formation of hydrogen sulfide with this process called sulfidogenesis. This H2S is the odorous gas, like some rotten egg, okay, that we can have in anaerobic reactors. This is a problem for us, but we can't avoid the formation of this gas. We have to deal with the formation of this gas with other means. We will see how we can do this to control the odors and to control the corrosion problems as well in the system, okay? When you have sulfate in your wastewater, in the raw wastewater, you will have sulfide, okay, in your system. You can't avoid that. You have to deal with that, okay? There we have the generation of methane and the generation of hydrogen sulfide as well. Regarding the COD balance in
Eric,
anaerobic
Eric,
systems, see?
Eric, excuse me. There is a question from Redford about the diagram, I think.
Okay, Rensford, we if you have a quick question, we can see it, or we can wait on the end of the session. So please tell us what is your question.
The hand is down right now, so maybe to the end of the session.
Okay, I'll maintain the question at the end of the session because we have a lot of material to see. Okay, but please note, write down every question you have. I'll try to listen to them at the end of the session. Okay. Okay. In this case, we will have a balance of COD, or a COD balance of the system for anaerobic reactors. Look that.
We can see the presentation. We can.
Okay. I'll share it. Sorry. It's okay now?
It's okay now.
Thank you, Luis Diego, I'm sorry. Okay, so in this case, from the organic matter entering the system, here measured as total COD, we will have a part that is not biodegradable, so we call it recalcitrant COD. This will remain in the system. This can't be digested by an anaerobic digestion normally. We have a fraction that is biodegradable COD. In this case, a small part will be transformed in sludge, as we already saw, and the other part will be transformed into organic acids. From these organic acids, we will have the methane, COD transforming methane. This is the biogas we want. Another part will remain as acid COD, organic acids that did not react, and another part that we don't want but we can't avoid will be transformed into H2S. So this is a balance of the COD of the system. Normally you will have this in every kind of reactor. Okay, this is the fundamentals of anaerobic reactors. You have different environmental conditions for the system. You have requirements of temperatures. Look that the ideal conditions are temperatures in the mesophilic range between 30 to 35 degrees. In any case, you need more than 15 degrees to work with anaerobic digestion. So this is normally you can work with 20 degrees perfectly. Above 20 degrees is a great range of temperature for anaerobic digestion. So this temperature is just the temperature in our region. So we have perfect conditions for anaerobic digestion in the Caribbean and in Central America. Okay. Normally you have to avoid sudden changes in temperature that can affect the system. The more sensitive bacteria or microorganism is in our system are the methanogenic. Okay, they are very sensitive, so many things can affect the methanogenesis, and we will have the fail of the system. We must have enough nutrients, nitrogen, phosphorus, sulfur, and many other elements in small concentrations, In the case of municipal wastewater, normally this is not a concern. We have in our sewage the different elements in the perfect proportion. So this is not a problem for us. This is a problem more for industrial wastewater, okay? Also the pH must be between 6.5 and 7.5. Normally for, again, for wastewater, for sewage, this is not a concern. It could be in some cases for sludge digestion, as we will see, and we have to provide alkalinity, okay, in some cases. And as I already said, methanogenic are very sensitive. Many of these nutrients in higher concentrations can produce toxicity in our system, in the methanogenic microorganisms. So we have to control the entry at the inlet, at the system inlet, the concentration of some systems. Normally, again, for wastewater, for sewage, this is not a concern. We don't have normally very high concentrations of these compounds or heavy metals as well. This can be a problem when you have in your sewage in your sewage network in the sewers a lot of companies or industries that are discharging their wastewater, industrial wastewater, into the network. Normally you will have in your country some regulations to avoid that, okay? They have to pre-treat the wastewater at least. And in my experience, for example, at least for Costa Rica, this is not a concern even at the larger wastewater treatment plant where you have more industrialization. The dilution, the effect of the dilution is really, really important. You don't you don't attain these limits of toxicity. In the different material that I gave to you, you can see the specific concentrations. Okay, you can consult these sources to see what is the limit for the different cations or heavy metals that anaerobic systems can't resist. Okay. Okay. Later to next to the digestion, to the use of anaerobic digestion in wastewater treatment, we will see where in our system we can have these processes and which kind of reactors we can use. We have two main points or two main processes in our sewage treatment plants where we can use anaerobic digestion. The first one is the digestion of sludge. So we will have sludge digesters. And the second one, more newer than the last one, is the digestion, the anaerobic digestion directly of the wastewater. Okay. In one case, we are digesting the sludge. In the other case, we are digesting the wastewater. They are different. In the first case, anaerobic digestion of sludge, there you have a process flow diagram of a typical wastewater treatment. Normally for large sewage treatment plant, you will have the pretreatment, you will have the primary treatment with primary settlers. There you will produce primary sludge, and after the primary treatment, you will have the secondary treatment. Normally we call it biological treatment. In this process flow diagram, normally you will have activated sludge, for example, with anaerobic aeration tank and a secondary settler. In the secondary settler, you will have secondary sludge. In this case, this is biomass, okay, biomass that settles in this system. And you can also have a trickling filter that is also a biological aerobic treatment with a secondary settler. Notice that in this diagram, you will have two very different kinds of sludge. You will have the primary sludge in the first settler. This is not biomass. This is solids carried by the raw sewage that will settle in this unit and will be transformed into primary sludge. And we have also secondary sludge. The secondary sludge is biomass, okay, biomass that consumed the soluble organic matter, and they reproduce themselves to generate secondary sludge. We have to deal with this sludge, primary sludge and secondary sludge, and we have, along with the line of water treatment, we have the line of sludge treatment, solid treatment. Normally, we will have a thickener to reduce the humidity of this sludge, and there we have our anaerobic digestion. In this case, we will take the sludge, primary sludge. It could be only primary sludge. It could be also a mix of sludge, primary and secondary, and we will digest this sludge to produce biogas, okay? So this is part of the sludge treatment. We do this, we will see why, but this is the treatment of the sludge, not of the water in this case. Normally, especially the primary sludge, this has the primary sludge is highly putrescible, so it can get rotting really easy, okay? Because it has a relation, a ratio of volatile solid and total solid of 75 to 0.8. So we have a lot of volatile solids here. When these volatile solids go, for example, to landfills, it could get rotting, and it will attract vectors like rats, like flies, like other vectors, and produce other problems as well. So the objective of the digestion, in this case, for the treatment of sludge, is the biological stabilization of the organic matter. We will reduce this ratio of volatile solids and total solids to a much lower level. In this case, we could do it also by anaerobic treatment, anaerobic digester. In this case, we will need the injection of air, so we will need a lot of energy. In the contrary of anaerobic digestion, and by those processes, the digestion of sludge, it could be anaerobically or aerobically. The idea is to stabilize the anaerobic matter, these volatile solids, and in the case of the anaerobic digestion, at the same time produce usable biogas, okay? A diagram of anaerobic digestion. Normally, you will have an enormous tank where you will let the sludge enter in the system. We'll have a mixing system, and the anaerobic biomass will be there to stabilize the organic matter. You will have the formation of biogas and the exit, the digestate that will be stabilized. Later, after the digestion, you will need to proceed with your treatment, for example, with the watering of the sludge, or with drying of the sludge also is possible, and its disposal or use in normally in agriculture, okay? You can have only primary sludge, you can have a mix of sludge, primary and secondary, and in some cases, you can even have the co-digestion of different substrates, okay? We will see that later. Okay, there you can also inject in the system fats removed from the degriter unit, okay, degriter and removal of fat unit in the system of the wastewater treatment. You can also have some pre-treatment for the sludge to increase the gas production. Those are topics of research, particularly in Europe, and this process is also used in our countries, normally in the larger plants, okay? For example, in Costa Rica, we have this in the plant for San Jose, the capital of the country, but also in Nicaragua for the Managua, the plant in Managua, the larger of the country also. We have also cases in Chile, Brazil, and I'm pretty sure that you already know also cases maybe in your countries for this system, okay? The question of this system is that it can be interesting or attractive for only larger systems, larger scale systems. Normally, and this number will vary in the literature, up to 30,000 equivalent inhabitants, okay? This number can vary between, depending on depending on the sources that you are reading, between something like 20,000 to 50,000. After this population, normally the cost of the anaerobic digestion is covered by the use of the biogas, okay? And it becomes more interesting. After the digestion, you will need to dewater the sludge, okay? And you can use it in the agriculture as well. You have different anaerobic reactor for sludge, for the sludge digestion reactors. You can have normally a cylindrical shape or R egg shape. That depends a lot on the provider. Some of them work more with cylindrical shape. Some other work more with the egg shape, telling that this system brings a better mixing of the reactor. Okay, normally you will have an agitation, mixers in the system to make it more efficient, and sometimes you can even recirculate for this to make this mixing possible, recirculate the sludge or recirculate the biogas. Okay, there are different possibilities in this case. There you have how to design the volume of the system. Normally, you will need to calculate the production of volatile solids. Okay, with this table you can do it, knowing, for example, the per capita production of total solids in this case in the primary settler, knowing the number of inhabitants, you can multiply that this ratio by the unitary sludge production, have a total mass of solids, use these typical values of volatile solids, and do the math to estimate the required volume. We will see later how to estimate the production of biogas as well, okay? The other case that can be very interesting for our region is the direct digestion of the wastewater. In this case, we will have also the pretreatment as in the later case, but later we will have anaerobic reactors for the liquid phase. In this case, we have 3 different examples of anaerobic reactors. We will see a lot more of them. And we will produce the biogas directly from these reactors, okay, from the water treatment, not from the sludge. We will have also sludge production in these cases. We have to adequately treat this sludge. We can't produce more biogas from this sludge. We have to dewater the sludge and dispose of the sludge. But the biogas is produced from the liquid phase. And regarding the liquid phase, we will have to give a post-treatment, okay? Normally anaerobic post-treatment of the liquid phase as well, okay? In this case, as already said, normally we will need a warm climate, okay? Temperatures above 15 degrees all the year. So this is exactly our case in Central America and the Caribbean, okay? This technology has been used in many countries, in warm climate countries, Egypt, Mexico, Colombia, Brazil. Brazil, as I already said, is the country with the more population treating their wastewater with this technology, more than 20 million inhabitants, and they have a lot of research and advances in this topic. Okay, so we can say that for our region and for warm climate countries, anaerobic reactor treatment of wastewater is a mature technology, okay, for removing organic matter. Normally, you will need a post-treatment, anaerobic post-treatment, and you will have production of biogas as well. In the case of the treatment of wastewater, here we have two systems, just to make a comparison. In the first line, we have the standard aeration activated sludge. This is a really used system, at least in my country. We have done some research and we saw that more than 95% of the system operating in our country is this technology, okay, and activated sludge. On the contrary, we can have an anaerobic reactor, in this case, an ASB reactor, followed, in this case, by a trickling filter. This is anaerobic treatment, post-treatment. In the first case, we will have consumption of energy. Look that here we need 25 kilowatt per habitant per year, okay, because this system will need aeration, different kind of aeration. It could be surface aeration, it could be aeration in the bottom, it doesn't matter. It will consume energy, electricity. On the contrary, the anaerobic reactor, at least for the biological treatment, will not consume energy. Okay. On the contrary, it will produce biogas, which is energy. So when you are selecting the technology for your system, you have to be careful because some system will need energy. In this case, okay, other system will not need energy and could even produce. Has to be considered during the technology selection process. According to the Brazilian people, the operation of this anaerobic system would up to 10 times lower than the first one. The problem is, or the anaerobic system are more new, are not as wide spread as activated. This system will work small scale or in very large scale. In Brazil, you have systems for communities. I would say with this three process flow diagram, okay, with USB reactor and trickling filter, and you have also plants for more than 1 million, okay, working in Brazil and generating biogas. The production of biogas will be approximately proportional to the population served, and depending on the anaerobic reactor, the capture of this biogas will be more and less sample. Okay. Regarding the different anaerobic reactors, here you have some pictures or some diagrams of different possibilities. You will have extensive reactors, extensive in area, with a huge footprint like anaerobic lagoons. There, the capture of the biogas would be harder because you have to cover your lagoon with normally a membrane and capture the biogas, but it is possible. In the case of municipal wastewater, this is not so common. Okay, the anaerobic lagoons. You have also compact reactors, so they are much lower in footprint. Many examples are available in the literature. For example, anaerobic biodisk. I have never seen this in operation, but it exists at least in the literature. You have also upflow anaerobic filters. This is very used in my country and also in Brazil. Okay, you have the flow from the bottom to the upper part of the reactor and a packing medium, for example, stone, okay, or plastic in some cases. You can have the flow from the upper side to the bottom. In this case, downflow anaerobic filter. Other reactors, such as the fluidized bed anaerobic reactors, have two-stage anaerobic reactors. All of them are compact units. They gaining interest anaerobic reactor, okay, as well, is another possibility. This one, we will see this more in detail, the upflow anaerobic sludge blanket reactor. Okay, there you have no media, no packing media. You have only the biomass in the bottom, okay, of the system. You can have also expanded granular sludge bed reactor. This is not possible for municipal wastewater. It is for industrial wastewater, depending on the characteristic of the wastewater, okay? And many other different adaptations or private systems, okay, that are available in the literature, okay? In the case of USB reactor, which are the most used in large scales, okay, or in number of systems in Brazil and normally in Latin America, you will have the flow entering in the bottom of the system, going through a very dense sludge bed, very concentrated. Later, the flow goes to the upper side of the system through a sludge blanket, less dense than the sludge bed in the bottom, and you will have a structure here, an element called three-phase separator that should be well designed, adequate. This is a really sensitive topic, and the water entering here to the settling compartment to go to the post-treatment, okay? This three-phase separator will separate the biogas that will be captured here in the upper side of the three-phase separator, the solids that will go back to the digestion compartment after going to the settling compartment, and the liquid, okay? There are very compact units with hydraulic rotation times between 8 and 10 hours, okay? Remember that, for example, lagoons, you will have many days, maybe something like 5 to 10 days of hydraulic rotation time. So this unit is much more compact than anaerobic lagoons, and it does not consume energy. It produces biogas, okay, on the contrary. Sludge age above 30 days. If you want more information on the design of these systems, you can consult Chernicharon Bersani. This is a really recent book, really well written, with all the information on the design, operation, and construction of these reactors, okay? There you have some pictures of anaerobic reactors. You can have it of the kind, okay? It could be circular in this case, okay, very compact unit. This unit was in the experimental field of the Federal University of Minas Gerais, where I did my research for my PhD. This unit could be used for something like 150 inhabitants, okay? When you have larger systems, you have to construct or design systems better for making a better use of space. So they will be rectangular, okay, prismatic, and they will be one at the side of the other, okay? In this case, you have the USB reactors. This plant could be for like 50,000 people, okay? And all the pipe tubulation details can be or should be consulted in the literature, okay? There are a lot of details, but this is a really well-studied system. Many advances have been done in the last 20 to 30 years, and now I can say that they operate much better than they did in the past, in the first experiences in Colombia in the 90s, okay? Regarding the biogas, we already know where in our sewage treatment plant we can have biogas. Now let's give some characteristics of that biogas. Normally, when you don't have a system, an existing system, you have to work with mass and energy balances to estimate, okay, in the design phase, for example, what amount of energy you can obtain from your system. In the case of sludge digesters, normally you will use the volatile solids. In the case of the liquid phase reactors, normally you will use the chemical oxygen demand. you could use both, okay, in any case, but I don't know the use the experience, the different references tend to use volatile solids to sludge and COD for liquid phase. In the case of sludge digesters, the mass balance would be something like this, okay? You will have the volatile solids entering the system. Normally, you will consider a destruction of volatile solids of around 40%, and the destroyed volatile solids transformed or converted to biogas. Normally, 225 liters per habitant per day of biogas. So this is a rule, okay, thumb rule, a number that you can use for your first estimation of energy production from the sludge digestion, okay? Normally, you will need to do more sophisticated calculations that you can find in the literature as well. In the case of the liquid phase reactors, the balance will be done on the COD parameter of organic matter, okay? In this case, you have to consider all the kind of COD at the end of the reactor that you will obtain, okay? Remember that only this COD, methane, will be transformed in methane, in biogas, okay? So it can be hard. Also, a problem that I didn't mention before is that of this COD, of the methane that is produced in the anaerobic reactor, a huge part of this methane will remain dissolved in the liquid phase. So I will not recover this methane in the biogas. It will go out with the liquid effluent. Something between 30 to 40% of the total produced methane will go with the liquid phase. This is a problem in these systems. I will talk about that later in my presentation. Okay, so Brazilian people has advanced a lot with this kind of problems. For the case of anaerobic reactors in the liquid phase, they have a tool, a digital tool that we can use for preliminary design process, okay, to estimate what would be the production of biogas in our systems. They also have studied the variation of the biogas production in their plant. So look, in this case, in a normal day of operation of anaerobic reactor liquid phase, look that we will have a variation during all the day. Some points, some hours of the day, some moments of the day will have a peak of production. Other we have a lower production flow of biogas. Okay, in this case, this will be the fluctuation when we don't have rain. Okay, when we have rain in our system, the production will go down as well. Okay, so there are some limitations that should be addressed during the design of the system of biogas. So from the research from the Brazilians, they have estimated some scenarios of typical production of biogas for the anaerobic reactors, USB reactor in this case. You can use it as a reference to estimate what could be the production for your own systems. We have three scenarios: pessimist, typical, and optimist scenario. It depends, for example, on the entrance of inflow. Okay, for example, rainwater into the network, or also it depends in the concentration of sulfate. Okay, in the raw wastewater. Remember that sulfate will be transformed into hydrogen sulfide and will reduce the production of methane. We have a typical scenario and an optimist scenario. So for typical conditions, normally you could expect something like 10 to, here you have the average value, something like 13, 14 liters of biogas per inhabitant per day, okay? Those are typical values, you can consult this article from Livia Lovato from her PhD research, and this can be used as first numbers for your calculations, okay? There are a digital tool available also. You can download this tool in this website. This tool is in Portuguese. This is not available in English or Spanish for the moment, but it's really intuitive to be used, okay? You have to complete the population or the flow, entering the system, put some data, for example, the COD in the influent of the system, and then you can choose some typical conditions, some pessimist condition, some optimist condition as well in this screen, or you can put your own data as well, concentration of sulfate, concentration efficiency of removal of COD, all that, and the system will automatically calculate the balance of the mass balance of the system and the energy balance. So look that in this case we have COD in the effluent, as I already said, something like 16% of the total COD at the entrance will be transformed, will remain dissolved in the liquid phase. So the system does all the calculation, and at the end, for this example, you will have something like 47.7% cubic meter per day of biogas, okay, of methane in this case. Biogas would be up to 70 cubic meters per day, okay? So we have some digital tools available to do our first calculations in a more detailed way, okay? The second version of this tool, ProBio 2, will be available soon. In this new tool, you will be able to calculate, for example, how much energy could be used in a boiler, for example. So it would be more complete than the first one. Regarding the qualitative aspects of biogas, in this table we can see for sludge biogas and for municipal wastewater biogas, remembering that this one is for the liquid phase only, that we will have many different compounds in our biogas. The most important would be methane, of course, but we will have two different biogases. Okay, in the case of sludge, the concentration of methane will be lower. It will be more concentrated for the liquid phase biogas. For sludge, the concentration of carbon dioxide will be much higher. Okay, this is related to the thermodynamic of the system. I will not go further in this topic because this is complicated, but these values have been observed in the plants. Okay, see there, for example, for H2S, the concentration will be very important in both kinds of biogas, a bit higher for municipal wastewater biogas. Okay, we have also some compounds such as this one, siloxanes. Siloxanes are compounds of silica, okay, that will produce problems in different equipment. We will see this later, okay? And of course, we'll have the calorific value of biogas, which is related with the methane content of the biogas. So normally we will have really interesting percentages of methane in the biogas. Okay, all of the equipment that you will find in the market will work fine with this methane concentration normally. Okay. Regarding the biogas, we have to make a point on the hazards, okay, of the biogas. First, the explosivity risk of methane when it gets mixed with oxygen from the atmosphere. and also the hazard related with hydrogen sulfide. In the case of methane, when it gets mixed with air and it reaches concentrations between 5% and more or less 15%, we will be into the explosive range of methane. Okay, so in this case, there is a risk of explosion that should be addressed during the design of the system as well and during the operation. The objective is to never attain the lower explosive limit. Okay, never attain 5%. So to avoid the mixture of methane with air. This is normally really easily attained in wastewater treatment. I have never seen, at least for wastewater treatment, reports of explosion or risk of this of that kind. Okay, and of course the training of the staff, avoiding, for example, smoking in the plant or any kind of fire, okay, or ignition sources that should be making or putting in risk the system. Regarding the H2S, here we have some different hazards or concerns. The first one is a concern of disease or even death. Okay, H2S at very high concentration is really toxic. It could produce the death of the people for concentrations up to 100 ppm in volume. This only happens inside the three-phase separator or inside the sludge digester, okay, or in the gasometer. This is the reservoir of gas. So these points are really dangerous. Okay, never the operator can go there, okay, without the proper measures, okay, of safety. Also, another problem related with sulfide is the corrosion of concrete and steel. Concentration really low, such as 10 ppm, will produce the corrosion of concrete and steel, and of course the the rotten egg problem, other okay of H2S at concentration as low as 0.4 ppm. So this is a concern for the neighborhood as well. That should be addressed during the design of the system. Here you have some pictures of the corrosion by the H2S. Never put metallic systems close to metallic structures close to anaerobic reactors. You have to choose other materials like fiberglass or plastic. Okay, concrete as well. You have to protect, if your structure is of concrete, you have to protect the cover of the concrete. You have to put some kind of line, okay, to protect the concrete. Many of these topics, all of them indeed, are addressed in the technical notes of that I gave. Did a really good work for all these topics. In the case of the other, normally you will need another control system when you have neighbors really close to the plant. This is not very expensive. We normally recommend biofilters to oxidize the H2S, okay? And it's really easy to operate as well. Okay, we already know how our biogas will be, okay, which are the characteristics of our biogas. Now, let's see how we could use this biogas that we generated in our in our wastewater treatment plant. We need different units for the biogas, just like with the liquid or the solid phase. We will need a treatment of biogas, so a line of treatment of biogas. In this case, we have the transportation, the capturing, transportation, and storage of biogas with these very minimum elements for our system: a hydraulic seal, We will see what is this in the next slide. Some security elements, flame arrestor valve, isolation valve. Also, the biogas is saturated in water, so we have to install drains, okay, in the system. Overpressure valve as well for security. Very important for our system, biogas meter and the gasometer, the gas reservoir, okay? And at least also a biogas flame, okay, or burner. This is the very minimum because biogas, uh, remember that is composed is by methane. Methane is a really important greenhouse gas, okay, up to 28 times the CO2. So if you can't use the biogas, you have at least to burn it to avoid its discharge into the atmosphere. Okay. There, in the case of the sludge digester, you have remembered that for systems of larger scales, you will have all the process flow diagram for your biogas with some elements, for example, foam control system, filter, the biogas flow measurement device, the gas holder or gasometer as well, and many elements, details that should be present in the system. The equipment should be ATEX equipment, so special or specific for explosive atmospheres environments, okay? Because there is the risk of production of ignition source and explosion. So they are more expensive, they are more safe as well. All this information is really complete in this document from Brazil in Portuguese, the PROSAP. I gave this to you as well, okay? Later, for our system, for the liquid phase, this is the really minimum elements in our system. You will have the hydraulic seal in this case. This will pressurize the pipe, the biogas pipe, the biogas flow meter, the flame arrestor, the drain, and the biogas flare or torch, okay, to burn the biogas. Sometimes it could be recommended, okay, it should be a good idea to install only this part of the biogas system to monitor during a couple of years the biogas production, okay, to be sure that what the production should be in our system, and then to design and construct, install the biogas use system when you have data, okay, because you can do the math, you can do the mass balances of the system, but never you will be completely sure of what the real potential of the system is in terms of biogas production. When you have real data of your system, it could provide more safe information for your design, okay? So this is the really minimum elements in your biogas treatment system. Regarding the storage of the biogas, there are different gas holders or gasometers uh, uh, available in the market. Okay, more information in ProSap. There you have some pictures. These double membrane systems are really normal at larger scales. Okay, you have two membranes. In this case, a membrane that will retain the biogas and a second membrane that will be with compressed air. Okay, and you have also for smaller systems this inflatable tube, okay, that could also hold the biogas. When you already have your holder, okay, the holder, the biogas holder is very necessary because you already saw the biogas variation during the day, okay? So the biogas will fluctuate, the biogas production will fluctuate during the day or during the time. So you need a compensation unit, in this case, the biogas holder, because normally your equipment will need a continual source of biogas. So this is the function of the biogas holder. Really important to use the biogas. Okay, regarding the possible uses for biogas, biogas is a really rich gas in methane, as we already saw. Methane is a hydrocarbon with a high energy potential, okay? So we have biogas with methane in the form of chemical energy. It could be transformed in other forms of energy, normally mechanical energy, thermal energy, or electrical energy. For the different design process, you will use energy balance. Normally, a chemical engineer, a process engineer, or a mechanical engineer will do the math to study the different possibilities for using the biogas. There you have a figure that shows the different possibilities of biogas energy transformation. Remember that biogas is in the form of chemical energy. It could be used in that way, in that form, okay? For example, as fuel for vehicles, we will see this. We can donate this biogas for third parties, for example, for cooking, okay? Or in developed countries, in Europe, for example, in Brazil also, they do this, injection into the natural gas network, okay? In the other side, we can transform in our sewage treatment plant this chemical energy in thermal energy, for example, with boilers or with sludge dryer systems. We can use also generators to produce electricity, okay, and use electricity and thermal energy cogeneration, or even we can use the biogas with turbines to produce gas rotary, to produce mechanical energy with gas rotary machines, okay? We will see some examples of this. The first example for recovering heat is in our sewage treatment plant is using the biogas to by burning it into the plant, into the wastewater treatment plant, and heating some fluid, normally liquid or gas fluid. It could be water, it could be oil, and produce heat. This heat can be used in an industrial company, for example, for boiler. In any industry that has a boiler, you can use the biogas as an energy source, okay? In the plant, it could be used, for example, for heating the sludge. We will see this, okay, in the next slide. And normally, for using the biogas into a boiler, you will need to reduce at least the humidity and the H2S. So you have to treat the biogas before it. There you have some examples of use of biogas for heating, okay, in after burning the biogas into a boiler, in this case for heating the sludge digester for the sludge treatment in anaerobic digesters. In this case, they put some pipes that will transfer the heat of the liquid inside the pipes to the sludge, okay? This is really normal in European countries where they have colder climates than in our region. Normally in a region, I don't know, at least in Costa Rica, this for the anaerobic digesters. Normally the ambient temperature is enough, okay, for the digestion, but it is a possibility. Another interesting possibility in our systems is using the biogas into a sludge drying system. In this case, the system generates really hot air, okay? And this really hot air, the gas produced by the combustion of the biogas will heat the sludge. Okay, in this case, you can reduce the sludge volume, a really important reduction of the sludge volume, and you will also obtain the sanitization of sludge. Okay, so you are converting your sludge, normally dewatered sludge, into a biosolid that should be used into the agriculture. Okay, in this case, normally you have only industrial dryers, so really big equipment that you should use only at large scale systems, but you can use, for example, in this case, into a drying bed, a system for heating sludge, okay, also using the biogas for small, in this case, for small scale systems, for small scale plants. Another possibility with biogas generated in our plants is the production of electricity. In this case, you could use electricity into the plant and at the same time using this exhaust gases, that is the gases produced during the combustion, to recover heat, okay, as well. So you will have the recovery of electricity and the recovery of heat in CHP systems at the same time. In this case, you can have a production of electricity between 30 to 40% of the methane energetic value, okay, and the recovery of heat of something like 30%. So you are recovering up to 90% of the total energy of the biogas into electricity and into heat, okay? There are really small equipment available in the market of down to 5 kilowatts, okay? So you can use this in small systems normally, okay? Not too small, but something like uh, thousands of thousands of inhabitants in your plant to produce electricity. But before, you have to remove, and this is really important for these systems, remove the H2S, moisture, humidity, and siloxanes from your biogas. The problem of siloxanes in these units is that when you have the combustion, the siloxane, which is silica, will be converted like in a type of glass. You will have like a vitrification of siloxane into your system, and it will affect your equipment in the large term. Okay. Another possibility for generating electricity are gas turbine. Normally, from the study of the Brazilians, they recommend more this equipment, the gas engines, for a region than gas turbines. They are more expensive, but this is another possibility that should be explored uh, during the design process. Okay, this work uh, really this work like a turbine, which work with the exhaust gases of the combustion, and as with the CHP, you can recover electricity and heat as well. Okay, in the case of the electricity generation, normally you can have different scenarios. In systems with lower demand of electricity, the electrical energy will be enough to satisfy the demand of all the plant. So in this case, you can even sell the surplus energy to the electricity grid if it is allowed in your country. In Costa Rica, it is not allowed for the moment, okay? And if this is not the case and the demand of the system is larger than the production of biogas, at least you can use the biogas for the peak hours when the electricity is more expensive, okay? For example, in the morning. So you will reduce the cost of operation of your system. Another possible use for biogas, which is really a trend in Europe, is the use of the production of biomethane. Biomethane is a purified biogas where you remove, for example, the CO2 and the oxygen and other compounds to concentrate the methane. So you will attain concentration of methane between 90 to 95%, this is just like natural gas, okay? So we are producing natural gas in this case, which can be used in the vehicles of your company or buses or trucks, okay? So in this case, we are producing natural gas. When it comes from the methane, we call it biomethane, really used in Europe, okay? Another possibility when you have your biomethane is to introduce it in the natural gas grid. Okay, I don't know. Maybe in some of your countries you have natural gas grids. In Costa Rica, this is not this is inexistent. Okay, but a possibility is to generate biomethane in the plant. Remember removing the CO2 and purifying the biogas, and then selling it to the company of natural gas. Okay, it could used in industry, in households, or as a fuel, as we saw. Another possibility that for smaller systems, and I think that this could be really interesting in our countries, is just donating the biogas, after removing the humidity and H2S, donating the biogas to the community so they can cook or heating water, okay, locally, just next to the plant, okay, in the neighborhood. That is a possibility. So if you want to use your biogas, you will need to treat the biogas before. You have to remove some compounds like humidity, particles, H2S, siloxanes, and if you want to produce biomethane, you have to remove carbon dioxide and nitrogen as well. This is very important. You have to meet the quality criteria of the equipment provider. Normally, this figure will give an idea of what you need, okay, depending on the use. Então, so see that for the biogas, you have to have the flare, the burner of the system, every time, but depending on the use of the system, of the use of the biogas, you will need to remove different compounds, at least humidity, but also H2S, siloxane, CO2, etc. Okay. For example, for gas engines, CHP, you will have to remove H2S and humidity and siloxanes as okay, to use these systems. For producing heat, normally you will have to remove humidity and H2S. Okay, it depends on the concentration of H2S of your biogas. So different equipments will have different meetings of quality. For the treatment process of biogas, this is a complicated topic. You will have different unitary processes and technologies that should be chosen and compared. Okay, you have different options for removing the moisture or the humidity, cooling, absorption, different techniques also to remove H2S, CO2, and siloxanes. You can see more information on this topic in ProSab, okay, from Brazil in this case. So let's see some examples of use of biogas in full-scale sewage treatment plants in our region, in Latin America. Okay, there are many different uses in the world, particularly for the sludge. For the sludge digester, I chose two examples from Latin America. The first example comes from Chile, in Santiago, the capital. There is a really known wastewater treatment plant. They don't even call it wastewater treatment plant. They call it biofactory, where they are recovering many different compounds from wastewater. It was constructed in the 2000 years, a flow up to 8.8 cubic meter per second. So these are really huge flow. At least some, I don't know, 3 or 4 million inhabitants, okay? A production of biogas up to 90,000 cubic meters per day, and they are producing biomethane in this case. There you have process flow diagram of the system, looked at in this case, as I already said, you have the sludge. The sludge is thickened, it is mixed sludge from the secondary treatment and from the primary treatment, and it is digested in anaerobic digesters where the biogas is produced. The biogas is treated, in this case with carbon, carbon filters, and converted into biomethane. More information can be seen or can be consulted in this link. The second case comes from Brazil. This is a smaller plant for something like 1 million inhabitants in Sao Paulo. The system is called wastewater Franca. In this case, they are producing up to 3,000 cubic meters per day of methane, and they are producing biomethane as well, and using it for the vehicles of the company. So all the company of Sabespi, which is the company of sanitation in this state, are using natural gas or biomethane for moving. Okay. Another example now for anaerobic reactors, also from Brazil. In this case, there you have the plant, in this case, for a flow of 360 liters per second. So something like 150,000 people, okay? In this case, you have the plant, the view of the plant. Look, those are the USB reactors there. There you have the trickling filters and the secondary settlers. And here at the bottom, the sludge treatment area where you have the centrifuges and you have the sludge dryer, and there you have the gasometer as well. There the gasometer, this balloon, okay? In this case, they use the biogas generated directly from the liquid phase to feed this sludge dryer, and they thermally dry the sludge. So they produce like a powder of sludge or small granules of sludge, and they at the same time sanitize the sludge. So this is a biosolid. It could be safely used in agriculture, and they reduce the volume of sludge as well. So in this case, the biogas is used inside of the same treatment process. I will present also a theoretical example of a study that we made in Costa Rica, in this case, to compare different possibilities of biogas use, in this case for a population of 10,000 inhabitants, so it's a small system, something like 10 liters per second, okay? And in this case, we compared at theoretically level the use of biogas for generating electricity, for cooking in the household, so in the neighborhood, for drying the sludge, as we saw in the last example, and for boilers, industrial boilers. In that region, we have the production of coffee and the production of sugar cane, so they normally have boilers that could use biogas instead, for example, lumber that is very used in our country. Okay, there you have the process flow diagram of the system, the population of Avangares in this case, the anaerobic reactor there in the liquid phase is in blue. Okay, we compared two different processes for the liquid phase. The first scenario, a scenario without treatment of the liquid phase. So we are using it directly in the agriculture. And a second scenario in which we removed some of the dissolved gases. I already said that a very important part of the methane will remain dissolved in the liquid effluent. So normally we should recommend, and we recommend the removal of these gases, at least methane and H2S, to treat it in a biofilter and to avoid the emission of methane, okay, to the atmosphere. In this case, this was scenario B, treatment of the dissolved gases, and scenario A, no treatment of the gases. We also compared different scenarios for biogas, as already said. Scenario 0, only burning the biogas. Scenario 1, electricity generation. Scenario 2, kitchen, using in kitchen, okay, to cook. Scenario 3, drying, sludge drying, and boilers, scenario 4. And part of the study also considered the use of sludge for agricultural fields or the production of a biosolid A, more quality, to be sold into boutiques, okay, into supermarkets, for example, as a really good soil conditioner for example, gardens, okay. There you have the results of the study in terms of economic benefits. In this case, you have the generation of electricity. In red, in orange, you have the substitution of liquid gas liquid petroleum, which is the gas that we use to cook, okay? This is composed by butane and propane, and other two uses, substitution of lumber in this case, and thermal drying, which were not really interesting from the point of view of economy. These values, so in this case, we obtained economic benefits up to 18 million colones. This is like $25,000 per year for the community. So they are getting some benefits from this practice, from using the biogas. This should be a really interesting option for them for accepting the plant. If we had used, in this case, activated sludge, which is the most used technology in my country, the results would be really different. The cost of the system and know the benefit, okay? So we have cost would be up to 25 to $67,000 per year in terms of electricity. So you see that with this kind of system, not only you are getting much lower costs, okay, but you are providing some sources of economic benefit for your population in this case. In terms of environmental indicators, we considered the carbon footprint. In this case, scenario A, without a dissolved gas system, scenario B, with dissolved gas system control, okay? In this case, we even attained neutral or negative carbon footprint plants for the use of gas for cooking or for substituting lumber, okay, for the boilers. So first, it is really important to have this biogas, this dissolved gas system control in the system. Look that in scenario A, the emission of the system is positive. When you added the dissolved gases control system, it became negative. And also, when you substitute fuels like petroleum or other fuels derived from petroleum, you will have negative, a really important mitigation, okay, or compensation of emissions. In the case of Costa Rica, for the electricity, we have a really friendly energetic grid, okay. Normally, all the electricity in Costa Rica is produced with hydropower or eolic or geothermy, but this could change in many countries, okay. Maybe in your countries, when you substitute the energy, the electricity, it could have a really important impact in the carbon footprint. It depends, it really depends on the characteristic of each energy grid, okay? Okay, some emerging topics for research, more for research than for application in different systems. The first one is the pretreatment for the anaerobic digester, the pretreatment of sludge. Some researchers are working on different methods to accelerate the hydrolysis that is normally the limiting step of digestion, anaerobic digestion. So you have some studies with thermal pretreatment, physical or chemical pretreatment, ultrasound pretreatment, which has for objective to break down the sludge and increase the percentage of destroyed volatile solids and increase the biogas production. So different providers would offer you different systems for that. Another possibility in the anaerobic digesters for sludge is the combination of different substrates, for example, fat, or for example, organic solids from households. Okay, for example, I don't know, fruits or different waste. In this case, the objective is to increase the volatile solids load sent to the digester and to increase also the biogas. At the same time, you are treating another problem, another waste, for example, from households. And in the case of the liquid phase, for example, USB reactor, this is a really incipient topic. We already don't know what could be the effect of doing digestion. For the moment, this is limited for sludge digester. Other topics of research deal with that part of the gases dissolved in the anaerobic effluents. Remember that between 30 to 45% of the biogas produced remains dissolved in the liquid phase, as well as with hydrogen sulfide. A good part of the hydrogen sulfide remains in the liquid phase. Both gases can be released downflow of the system and sent to the atmosphere, producing different problems, okay, environmental problems. Some techniques are available for at least recovering these gases and treating them for their oxidation, okay? Some new trends are being developed trying to recover that dissolved gas, okay, dissolved methane, and to use it in energy production as well, okay? There are some different possibilities. More information is available in this source. This is in Portuguese, are in Spanish as well, not in English for the moment. And at least we recommend for dealing with the dissolved gases, these systems, the simplified dissolution chamber and the packed dissolution chamber. They are really easy to operate and to design. You can see that in these resources. Other possibilities are possible for biogas, not only energetic uses. In some cases, the biogas or the methane could be used for the denitrification. This is a topic of research in the world, the DAMO process. And in some cases, the methane is being used as a source, as a material for producing high value added products. For example, for the pharma, petrochemical, and others. This is known as biorefinery. This is a really new topic of research in the world, okay? Other topics that have been or are being researched in the world are related to interrupting the anaerobic digestion, okay, and producing other products. For example, hydrogen. You see there hydrogen or organic acids, which are really valuable in some cases, okay? It could be used in pharma as well. From my point of view, these uses are more for the academic level for the moment and more for developed countries. So they are, for example, producing plastic. This is a really complicated or complex process from biogas. It is possible. from my point of view, I can say that biogas already has a really important value, energetic value, that is really easily usable in our countries. Okay, so for the moment, I recommend to focus in using biogas. Finally, to conclude, I would like to remember the role of anaerobic digestion in the sewage treatment and sustainability. From the Brazilian, they are of this idea that we should consider differently the developed countries and the developing countries, such as our countries in Latin America and the Caribbean. In the case of developed countries, sometimes different parameters like efficiency, reliability, sludge disposal, footprint requirements should be more important than they could be in developing countries. In our countries, they recommend that we focus on operating cost, building cost, sustainability, and simplicity. So the parameters for selecting the technologies in developed countries and developing countries should be different. We should focus on this, the cost, on operating cost is really important, okay, and simplicity as well, okay. With that in mind, we have different possibilities of plants. We have conventional wastewater treatment plants, for example, in this case, with extended aeration of activated sludge. In this case, we have the treatment of the water. Normally, we focused only on the water quality before discharging it to the river. We also have an important production of sludge that, in the best of the cases, is sent to landfills. Okay. In this case, we have a linear process. We only focus on the liquid phase, and we have a high generation of solids, a high energy consumption with the blowers in this diagram. This represent a high user fee, so we can tell that this is a not sustainable system. This is seen as a problem for the community. On the contrary, we should provide more sustainable systems, closing loops, cycles, okay, loops of the system. For example, by generating energy, as we saw, or by generating nutrients for agricultural fields. In this case, we can see the central role of the anaerobic reactor, low cost of operation, simplicity, and biogas generation. This is a sustainable system. It generates some byproducts that should be used in the community, and this could be sustainable. This could be maintained the time in our countries. There are different opinions or factors or parameters that should be addressed when we talk about sustainable wastewater treatment plant. Here we focused on gas, but there is also the solid phase management, the liquid phase management, and very important, the sewers management as well. Okay, all of them have been studied by the Brazilian team. I am citing there. They made really interesting publications. I really recommend you to try to read them, okay, and to imply them in your countries as well. Okay, to conclude, we saw that first anaerobic system with aerobic post-treatment, such as trickling filter, okay, should address or comply with the normally with all the quality requirements of our region, and it also has low operating costs. It generates less sludge and produces biogas. The biogas has a really high energy value that could be used in the communities. The other anaerobic digestion of the sludge process is also a possibility, really interesting for large-scale systems. And we believe that biogas, in this case, should be an engine to promote universal sanitation in the region. Okay, maybe this is a slow production of energy, but this could be really well used in our countries, in our region, to boost the indicators of sanitation as well. With this, I finish my presentation. I hope that you could understand the importance or the possibilities of biogas. I remain available for you if you have any question that could not be addressed in this short space of 10 minutes. You can send me an email and I will try to respond to you as soon as possible. Thank you very much for your time, for your attention, and I will ask Luis Diego to moderate the part of the question. Thank you.
Thank you very much, Eric. It was an excellent presentation, very technical, very professional. Thank you very much. So, as Eric says, someone has questions or comments about the presentation of Eric and the topic? Don't be shy. I also put the email of Eric in the chat. Amanda.
Hello, I'm from Guyana. I have a question concerning the UASB and the biogas. I want to know if we can capture the biogas from the UASB. We treat it to remove the carbon dioxide, the hydrogen sulfide, the water, and if we can now collect the biogas into like storage bags and then compress it into cylinders and can use that gas now for like cooking, like how we would cook with the propane gas from the cylinders. So I want to know how possible is that.
Okay, thank you very much for your question, Amanda. Yes, this is possible. This is technically possible. You can capture your biogas, treat it to remove, as you said, H2S, CO2, and to compress it, to put it into cylinders and to give it to families, even to sell it if you want. The thing here is that in the specific case of biogas from wastewater, you will not be able to remove the nitrogen. Okay, this is a really new topic of research: how to separate nitrogen from biogas. Sometimes you will have up to 20% of nitrogen in the system. Okay, in the biogas from wastewater treatment, not from sludge digester. But in any case, you will have the energetic potential there. Okay, so the families will be able to cook with this gas perfectly.
Okay, thank you.
You're welcome.
Thank you very much, Amanda. Joseph.
Just a follow-up on Amanda's question. How expensive, and you can look at this in terms of per capita, would an operation like this be? One of the reasons why we asking this question is that we are about to launch out on a project of that nature in a small community, fairly vulnerable community, right? And the funding that we have is not a lot. So while we want to do this, I just want to get a little guide as to the cost of such an operation. Not so much the capturing of the gas, but the removal of the hydrogen, water, and carbon dioxide, and the actual moving from that storage to bottling.
Okay.
That's an idea.
Okay, thank you, Joseph, for your question. Yes, always the cost will be one of the most important parameters of our systems. If you have a small community in a vulnerable community, normally the recommendation would be to use the biogas in the most simple way every time, as well as with the treatment process. Always think on the more simple way to do your work. Okay, in this case, if you want to use the biogas for heating, which is the most simple way for using the biogas, you will have to think about removing the H2S, So normally you will, for example, in a very simple unit, you will use a filter. It could be a filter of carbon, activated carbon, which is expensive. It could be a filter of ferrous oxide. Okay, we use here in Costa Rica residues of iron. Okay, for example, of I don't know, for example, from the iron industry or from the construction, you could use anything of iron to put it into a filter. This is not expensive, and there the H2S will be absorbed to the iron. You will remove the iron, and it could be then sent to the gasometer, to the reservoir of gas. For example, we have quoted from some biogas holders up to something like $200 for 3 cubic meters. Okay, so you have an idea of the cost of the gas holder, and for the use of the biogas, you have to think about the pipes of plastic or any other material to share the biogas with the community. Other possibility is to use the biogas into the plant. We are using a project in Costa Rica for research, in this case, with a cost of something like, let me convert it in dollars, $2,000, okay, for using the biogas into the plant to the sludge drying and to generate a sanitized sludge that could be safely used in the agriculture. So the cost will depend on each application of the system. You have to do the numbers. I think that with the tools you learned in this presentation, you will be able to at least identify the main elements of the system and then quote, because the cost will vary a lot from a country to the other, and see more or less what would be the cost of using this biogas. Okay.
Thank you. Thank you
very
for your
much.
answer. And I must say this is a very, very good presentation. Thank you.
Thank you, Joseph.
Indeed, it was a very good presentation. Anyone has a question? Well, thank you very much, Eric. Thank you all for being here. And this is the end of the session. We will have another sessions this week, and also a work about formulation of projects next week. So see you soon. Thank you very much.
Thank you, Diego. You have my contact anyway. Okay, in any case.
Yes, the contact is in the chat.
Thank you.
Also.
Thank you. You're welcome.
Bye.
Thank you.
Muchas gracias, Luis Diego, por el apoyo.
Vamos, Eric, súper bien. Muchas gracias.
Hasta luego entonces y quedo a la orden.
Luego nos vemos. Saludos.
Saludos.